Hi, my name is Hans Moritz Günther. I work at the Chandra X-ray Center at MIT in the high energy transmission grating group, where the high energy transmission gratings for Chandra were built and where we still make the software, the data reduction, and we do all sorts of things to help users use them. In this tutorial, I want to walk you through a Jupyter notebook where we reduce data for one specific science case. And I'll pick one science case. I'll explain the science case first with a couple of slides, and then we'll step through the actual commands that you would do to reduce your data. So I'll just give the intro about young stars here and see how that looks. So here's the Orion Nebula cloud. Stars form in dense clouds with gas and dust. And you see like bright stars over here, and you see these dust clouds around it. And then gravity will make all these dust clouds collapse and fall into each other, right? Um, and clumps will later be the stars, and then there'll be dust still around it. So the phases of star formation is that we have like a cloud like this, and we'll have like initial clumps here, and then they'll gravitationally collapse and compress whatever happens in the middle, and that infall will initially be radially. But because these clouds are never static, there's always some motion, some flow, and angular momentum is conserved, even if something moves very slowly at large scales. When you compress it, there'll be enough angular momentum to make it spin up. And so you'll have the source, the star in the center, and the star in the center will then be surrounded by an accretion disk, and this like outer cloud will fall onto the accretion disk, and then material will go along the accretion disk to fall into the star. And stars at this stage, a few thousand to tens of thousands or hundreds of thousands of years old, will blow out material in jets up and down and punch holes into these envelopes, and that's often how we see them. We'll only see them if they're punched in here. Um, that is the phase of planet formation. This is schematic, right? The disk doesn't actually reach down to the star, but we'll have this disk here, and in this disk, planets form. And eventually, planets may open these gaps by accreting material from the disk onto the planets. So let's say a thing like Jupiter will have high gravity, right, and sweep up all the stuff in this disk. And then, of course, this outer gas goes away. It's either blown out or photo evaporated, or it falls into the disk and eventually gets accreted in the star or the planet. And these disks are, of course, in capillary rotation around the star. And that is why in our solar system, all the stars, all the planets rotate around our sun in the same disk, in the same plane, because they're all formed in the same disk. And eventually, right, this disk also goes away, although we have some zodiacal light left in our solar system, but most of the mass of the disk is gone. And we'll end up with a system like our own, with like a star in the middle and planets around it. How does this disk look? Well, here's an image by ALMA from a star called TW Hya. This inner bit here is about 1 AU. So in here, like this would be in this inner clump here would still be the Earth. But you can easily imagine like a thing like Jupiter or Saturn or so opening up these rings, these gaps by taking things, right? By sweeping up all the gas and dust in it and accreting it. But you see that even though there's probably like some planet or here, there's still some connection, some material makes it through to this inner region that in our solar system, like Mercury and uh, the Earth and maybe even Mars, depending on what like, scalars would all sit like within this inner clump. So how does this inner clump look like? Well, we can't resolve that in imaging, but here are some simulations, right? Um, so here's a star. Let's look in the center. The white thing is a star. It has a magnetic field. These magnetic field lines here, these red ones, and it's rotating around. And then material falls along the magnetic field lines from this inner disk onto the star. And because it follows the magnetic field lines, it's not going to hit the star randomly. It's going to hit the star like mostly where the field lines connect to the star. And if you had a dipole-like field, it's going to happen close to the magnetic poles, right? And the exact structure changes depending on like which magnetic field lines carry the mass. This is a cut through from the side, and you see that it goes from the disk, like rises high, and then falls on the star and hits the star. It's essentially free fall velocity. How does that look in other wavelengths? And I'll show you in a moment how it looks in X-rays. How does it look in other wavelengths? Well, this red one model here, this is a non-accreting star, TW55. And then when you add this accretion shock, the material that hits the star, that hits the star with a shock. It's going to be heated up very bright. It makes a continuum here, and it makes emission lines. And if you add them all up, then you get pretty close to this black one is the data, which is the addition of several components, this red template model, this accretion model here, and this line model, and that's all, here's like a step in the middle, and that's all added together and shown here. It changes over time. Here's the same star observed at two different times. Um, taking out residual spectra here, the purple means the black is the data. The purple is the star, the underlying star that is without the accretion taken out. And so the purple should be just the accretion. You see the step here and you see these emission lines. And we can learn something from that about the accretion rate because all that energy needs to come from somewhere. It's powered by that infalling material. And then we can calculate the free fall velocity. We know how much energy each gram of infalling or each kilogram of infalling mass gives us. We can add this all up. We can integrate over it, and then we have an idea how much mass we need. The accretion changes the X-ray spectrum too. Like here's two stars. Here's again TW Hya and artist's impression how that might look, and a very similar star of similar age that doesn't have a disk. And in particular, I told you in the very, very beginning that we can use X-rays to probe the density of the emitting region. And we do that by comparing these, like neon in this case, these neon lines called the forbidden intercombination, the recombination line, R, I, and F. And you look at the ratio of F to I in TW Hydra, I is much bigger than F, whereas in a normal star that's not accreting, F is much bigger than I. And what that means is that the X-ray emission we see from TW Hydra is formed in a region of high density. Why? I'll get to that in a second. I first want to say that the accretion changes with time, and so we may want to look more than once. Right, here's the veiling, a measure for the accretion in time. So the average might be stable over, let's say, 25 years or so. But if you look at particular times, here it goes up, then we don't have any data that goes here, then it goes down, it goes up, it goes down. There's clearly structure to it. This isn't just random, right? It's not noise. I mean, this clearly goes up here. So what happens in the X-ray spectra? Well, I told you, like the diagnostic grating spectra, temperature, density, ionization, velocity shifts, a couple of other things. In this particular case, we want to learn about the density. Now, this is a Gaussian diagram. The energy is a slightly simplified version of the oxygen 7 or neon 9 triplet. So we have the ground state over here. And then electrons through collisions between electrons, because it's a hot gas, it's highly ionized. It's oxygen 7, there's only 2 electrons left. If it bumps into something like a proton, another electron, an electron can be excited to a higher state and then sits because it's forbidden. That means it sits on that for a long time. But we're doing astrophysics, so long time is not a problem for us. And in the ground, in your living room, right, you won't see that because other collisions would happen way before it falls back down to emit this photon. But in astrophysics, the densities are low. So it's going to fall down and give us an F line. Or if it gets excited to this higher line, a higher state, it would sit there for a while and fall down and give us an I line. Now, if the densities are just high enough, then the probability of it falling down before it hits something else might not be high enough. So some of these photons might get a second kick to get up to the second level, and then it'll come down through the intercombination line. So if the density is high enough, the F line appears weaker because instead of falling down, the photons get a second hit, get a second collision that brings them up here. The I line becomes stronger because some electrons that are initially excited to the F state would in fact, through a second collision, go over here and fall down the I line. So if you measure the ratio of F to I, that tells us something about the density. So here's an IPython notebook where we're going to run actual chow commands to look at actual Chandra data to get actual results. And I'll have some pitfalls, some traps, some things that are worth pointing out that I'll explain in between. Again, this is the oxygen neon triplet, the Gaussian diagram, and using X-ray spectra, we can measure things that we can't measure in low resolution spectra, like in this particular case, densities and temperatures. So the first thing we'll do is we'll get the data from TW Hydra. And to that, I'll simply go to the website, the Chaser website, where we find which ops IDs we want to download. Now, for the purpose of this tutorial, I've embedded that into this Jupyter notebook, but that's just so that I don't have to switch windows and screens in between. Obviously, you can open that in your web browser normally, in a separate page. So we're going to look for TW Hydra. We're going to resolve the name and then search. And here we go. Here's a list of 18 observations where TW Hydra was observed. You see all of those are taken as gratings. Most of those is the HETG. Here's an LETG one. Most of those are HETG ACEs. Here's LETG HRC. Now, I've been working on TW Hydra for most of my X-ray astronomy career. And so I know that many of those have been published before. So what we are going to do for this tutorial is we're going to pick up out one that hasn't been published yet and start with analyzing that. And so what I'm showing here, the code I'm showing is from a real science project I'm working on right now. And depending on when you watch this video, maybe the paper will eventually come out. And if you watch it shortly after I record it, then there won't be, it's new, right? So I don't have the answer. I don't know all the answers. I don't know what it means. This is a research project I'm doing. So this is as real as it gets. Okay, so there'll be 18 observations. Here'll be the ops IDs. And as I said, we're going to pick out an ops ID, one of the first ones that we find that hasn't been published yet. So we'll download the data. And you can do that in multiple ways. You can go through here, you can click on it, you can download it, you can save it with your mouse. In this tutorial, I'm going to use this Python commands in the notebook, in the Jupyter notebook as much as possible. And so with chow comes a package called chow contrib that has a number of useful tools. In particular, this run tool, which we'll see in a moment, that will allow us to install to run chow tasks like DM copy or all sorts of chow tasks from the Python command line. And it also comes with this download data ops IDs. So we're going to import those Python tools, and then we're going to download Chandra ops ID 13250. That is this one, and ACES LETG observation of 20 kiloseconds is that one. Well, the first one, I'm the PI of those, and one of those ones that haven't been published yet. Now, download Chandra ops IDs, and you just give it a list of ops IDs. In this case, a list is one, and then it's going to go and download it. And once it's done, it's going to report true. Now, if I do that through my Wi-Fi, it takes about 15 minutes to download. Of course, I could pause this tutorial and then start recording again when that is over. But what I've done is I've actually downloaded and saved it in the correct folder before running this notebook. And so what it does when I do download again now, it just checks if the files are already there. And if the files are complete, it doesn't download again. And that's just that so that you guys watching don't have to wait here for 15 minutes while nothing happens. Now, one aside that I want to point out is that chow comes with its own Python environment. There'll be Sherpa in it. There's this one contrib run tool and contrib chow contrib scripts in it. And there's a number of Python packages that are installed that they need, like common Python packages like NumPy. But it's a normal Python environment, and so we can install additional software into it that we want to use together with Chandra. And so a common one that many people might want to use is AstroPy. SciPy is another one, or maybe packages that allow you to work with optical data so you can work at the same time. And so I'm going to install AstroPy and Bokeh into that same environment. In fact, it turns out I already did that when I tried out that this notebook works before I started recording. But it checks which of the requirements and which of the requirements that AstroPy depends on or that Bokeh depends on what's already installed. And then pip will go out and install that from the pipe index. So what I want to do first is I want to get like a first quick look at the data using just like AstroPy and Python. Now you don't have to do that because we have chow. You can always use the full chow tools, but I want to show you different ways of looking at the same data because sometimes you might want to look at Chandra data without having like all the tools available, or you want to use Chandra data together with Fermi data or Chandra data together with ground-based optical data or Chandra data together with Hubble Space Telescope data. And sometimes you, for example, you might just want to look at things separately. So I want to show you how that works too. So what we are going to do is we're going to import an AstroPy table, and we're going to load the event files. The event file will have every photon in it that Chandra observed. And as you know, chow tools work a lot with manipulating that, but we'll just simply load that into a table and then look at it by hand. And so what we do as a next step is we'll bin it into a two-dimensional histogram of X and Y, make 1,000 bins. I want to point out that there's some commands in here that I'm not going to talk about detailed. So for example, here I'm loading matplotlib for plotting, and then I'm loading these M patches or matplotlib patches that I'll use later for annotation. If you want to have a matplotlib tutorial, you can go through and look at that in detail. But for now, I'm going to point out what's Chow specific or what's Chandra specific or what's particularly important. But if it's just to make a plot look a little nicer, you can look that up in the matplotlib documentation. So let's go ahead and do that and execute this cell and read that table. We've done that. And so here is a script where I'm going to make a plot. You'll see I make a figure, I make PLT subplots, and then I normalize that figure in some reasonable way and stretch it and do like a logarithmic stretch and stuff. And that's one of those things where I say I don't want to go over the details. Like you'll just have to go through and look at those yourself if you want to know. But this is a plotting code that will format and produce this following figure. So here we go. This is the data. You could have looked at that as DS9 or something, right? And all this complicated matplotlib code, what it does is like it draws these white boxes on here and makes these arrows and these annotations. Okay, so what we see here is the spectrum, the dispersed spectrum. Here is the main source, that's TW Hya. There's two chips. These yellow boxes, these dotted boxes here are the individual chips. Two of those are back illuminated chips. There's one over here and one over there. And the back illuminated chips have a higher rate of background. They're also more sensitive to soft photons. And that's why you just see higher signal there. The LETG disperses this way, and you see that the readout doesn't actually fill the chip because the sources can be relatively bright if it flares. And so the observer, in this case me, has chosen to only read out the inner part of the Chandra chip that covers the spectrum and covers some background region, because there's no reason why we need to downlink like all this, which will only contain background, because it's an LETG observation, so it's just a single line. It's not like this X shape that the HETG gives us. It's just a single line. And so reduce data volume and can accept higher count rates by virtue of having not observing or not recording the photons from these parts. Okay, there's other ways of looking at that. And so in the previous video, I showed these banana plots where we have the space X in one direction here. In one direction, that's just a location. So what this is, it's measuring in this direction in X in pixels or something like that, or in bin pixels. This isn't, by the way, this isn't straight here because it's not straight on the sky. That has to do with the angle that Chandra had towards the sun and towards the ecliptic at the time the observation was taken. But of course, we'll go and measure along this direction. We make it flat. So that's what's happening here. So you see the source here. Now you see the dispersed spectrum over here. And you see that we can, just very simple. I know Chow will be slightly more sophisticated, but we could just put like a white region down here and say, okay, all the photons in here, that's our source region. And then above and below, we take a background region. And again, Chow is going to be a little more sophisticated in picking out those regions. But in principle, that's what's happening. And the purpose of this tutorial is to explain first how it works in principle before we go and just run Chow tools as a black box without looking at every individual thing. Okay, so these are the same photons, except here we have the space in X here and the space in Y there. So this is an image. And now for this one, we look just at the photons in the source region. We show the space in X here. And then independent of if it's in this pixel or this pixel or this pixel or this pixel, we ignore this Y coordinate. And instead, what we put on this axis here is the energy of the photon as seen by the CCD. Because the CCD gives us a rough energy sorting and rough energy photon. And that allows us, again, to reduce the background further, right? So here in the center, here is a zeros order. So we see at this location, we see photons of all energies because it's not dispersed, it's just directly observed. And then as we go along here, that is this dispersed spectrum here. That's just the first order grading spectra. And you can see, this is the photons we want, and the photons down here, or the photons up here, over here, those are background photons. So by also filtering in energy and throwing out like these photons and just using the ones that are obviously here on the zeros order spectrum, Chow will give us a spectrum that has a much lower background than if we were just to use every photon that happens to be in here. This is the first order. Over here is like the second and third order, but you see, because the source is weak, they're relatively weak. And so we are not going to make use of those. So I've said like we can do that in Chow several times. And we can do this in Tract and Chow. But sometimes you might not have to do it in Chow because when you download a Chandra observation, and you it has like a source in the center and it's a grading observation, the standard pipeline will already extract all the products that you need. So you might just have to download the data and then go ahead and you have the ARF and the ARMF and the spectral, the PHA file that you want to use. And so that's all fine. And then you don't have to do anything. You just go and start fitting with those. There's also tgcat at tgcat.mit.edu, and there may be a separate talk about this, how to download data from tgcat, or you can go to the tgcat website, and there's a help section with talks on how it works. And again, you'll just get ready files. There's also Chandra Repro, a tool that's part of the Chandra distribution, of the CIAO distribution. And for simple point sources with standard settings, which this is, it's just a simple point source. There's no binarity, no other sources in the field that make any complications. We can just use standard settings and we could just run CIAO repro and then we'll get everything. And of course, you'll also have the option to run all the individual CIAO tools to find the source, define the region, do this energy cut here, extract the spectrum, make the ARF and the MARMF. You can also do that separately. So we're going to show some of those pathways below, but remember, like in many cases, you might have when you download the data, you might have what you want already to do the spectral fitting. One more word about running tools in CIAO, right? So many of our help pages and many of the documentations do something like this and assume you type it at the Unix command line. Let's say dm copy, some file, like some whatever part of it you want, some extension of it, and you filter it in a specific time and write that into a new file, and there be parameters, in this case, clobber yes, which means overwrite files if the output file, if it already exists. I prefer scripting in Python over scripting in Bash. And people are different. You can script all this in Bash. You can. And there's nothing wrong with that, and I've done that for a while. But I find Python more comfortable. So I'm going to use this run tool interface to run the same command on Python. And the equivalent command to this here, let me make that a little bigger so that's easier to read. The equivalent command to this here in Python is this. So RT, the run tool, DM copy, and then the first parameter, the second parameter, and the last parameter here. And so in Python, right, in the shell, parameters are separated by space. In Python, they're separated by comma. In the shell, you only have to make strings when it's complicated, essentially. Whereas simple file names, you can just type in, whereas in Python, that's always a string. And then if you set a parameter in Python, you do that with an equal. And in Python, we don't say yes and no, we say true and false. But if you can read like this version up here, then you can certainly read and understand what this version does, and it doesn't take a lot to type it. Now, why do I do that? Well, I'm using the power of Python now. One step smaller, make it maybe a little more, get a little more on the screen. Assume we don't want to go from 5,000 to 5,200 in time here, we want to go to some other time. We can calculate these values in Python now. We can do some Python, whatever we want to do. We can write a loop. We can calculate those numbers from some other observation, let's say from the observation time of tests or whatever we want to correlate it with. And then since this is just a Python string, we can plug them in here. And I find that very convenient. So that's just how we're going to call it. But again, if you wanted, you can rewrite it like this and type everything into the command line. Okay, so let's do something. And what we are going to do here is we're going to call individual CIAO tools, the most complicated way of doing it and the most flexible way of doing it, because that will allow you to set parameters that different from the default. Now, in this particular case, I said we don't want that. We don't actually need that, but I want to show how it works. I don't have to show a tutorial on how to download a file. Like you guys can do that. Okay, so we import the run tool. We did that above, but I typed it here again so that you see where it comes from. And then we build up. We use Python to make our file names. I use as root to S directory. I use the ops ID. The event file that we are going to start with sits in secondary. The out file we're going to call this. We need the aspect solution, which sits in the primary and has this name for that particular observation. And so we'll just set all these things. And then we'll call individual CIAO tools here. We call tgdetect2, which takes an event file. and writes a position file, a file with this source position it has found. We create a mask, which takes an event file, and take that source position that we just found, and write a mask file, like a region file that says which region are the sources and which region is source and which region is the background. Then we'll resolve events. TG resolve events is the next one. TG resolve events, where we will take this event one file, we write an out file, and we filter it for the region. And so that we tell the region what it is, and then it'll tell us if this is a zeroth order photon or first order photon or plus minus or plus arm or minus arm on the grating or no arm at all in the background and not in the region should be thrown out. We'll make a copy of that file, in particular that event file, this filter here, this is filter file, to make sure that we only use things that have the right time, and let's throw out the columns, the PHAs, because we don't need them anymore. That makes the file a tiny bit smaller. And then we run TG extract, which will take the output of this filtered file, this event2 file, as input into TG extract. And then it's going to write us an PHA2 file, a spectrum, which is what we want later. And in this particular case, we'll just do order -1 and 1, because as I showed you above, the high orders are barely visible. And last, we will make a response. So let's run that out, because it takes a little moment. We'll make response files. And the response files need the PHA file as input, and the event files, because it reads all sorts of information from the header, the observation time, because the response of the detectors changes with time. It reads the location on the sky and then propagates all this information to the event. So they're going to run a tiny moment. Probably should have pressed run while I was talking before. There'll be a bunch of output that we can look at, just as there would be output at the terminal. And as I've written down here already, there will be a warning printed that comes from the fact that we calculate here when we run mktgresp, make TG grading response. It does the R for every CCD, but every arm only covers some CDs, so some of them will be empty. That's okay, because we know they're empty, but it warns us nevertheless. Okay, so here's the output. We run it on my 8 processors. We make responses to the first and second order, and here's some of these warnings that we can ignore. We can also get a zeroth order spectrum, right? We can extract all these photons here and get a spectrum for that too. That may maybe help us fitting. The resolution is lower because it's not dispersed, but it doesn't hurt us to have that data. So let's list the regions in row 1 in the region file. This is where the location of that found the zeroth order source. I put it in a circle with these x and y coordinates and this radius. Okay, let's go and take a circle with this x and y and this radius and extract it and put it in files that are called zeroth order. Now, you may notice that I didn't specify anything for the background here. In fact, I commented that out. And that is simply because making the background takes a little while longer. And again, I don't want you to wait too long for this notebook, so we can get to the stuff that's most important. Okay, so we're running spec extract. It made an half and an arm F. And there we go. Now we have all the products. So we'll do some spectral fitting now, and we'll have some choice, right? We could use those files, those ARFs and ARMFs that we just made, or we could use the ones that came with the original download. The results won't be very, very similar. They won't be identical because the version of Chow that I use here is the most recently released version, where the stuff in the archive may have been processed like a year or two ago. And so the calibration gets slight tweaks, so the answers are going to be slightly different, but they're not going to be significantly different. So we'll pick one. I'm going to, in this case, even though we just made these files, I'm going to pick the one we directly downloaded because I think that's what most of you will use most of the time. So I should point out that typically when Chow runs the pipeline, it extracts orders -3, -2, -1, +1, +2, and +3. Although in our particular case, only 2 of those are useful. because only -1 and +1 have enough photons. So here's a question. Should we take all these like 6 and just merge them on top of each other and just have one spectrum? Isn't that a little easier to deal with? Well, it's certainly helpful for plotting, because then you only have one thing to plot on top of each other, and your plots are not as busy and have more photons and it's easier to see. But it's generally not recommended for fitting, because the different orders and the different wavelengths fall on different chips. So for example, here's the zeros order, the same wavelengths here and here falls on different chips, which have different properties. So you easily see that there's a background illuminated chip, so they have different ARFs, and that if different effective area curves, and that get statistically a little dicey. So it's better to keep them separate for fitting. We will, however, make a merged spectrum, which we will use for plotting. After we fit the model separately to the two files, the plots just look so much better. If you specifically have more orders, and you have the HETG, we have HEG plus and -1, MEG plus and -1, maybe plus and -2, maybe plus and -3. It's just hard to see otherwise. So let's go ahead and combine those spectra in a way, as I said, that we're going to use them for plotting. And now then I'm going to go ahead and load them into Sherpa for fitting. Now you could load them into XPack, you could load them into ISIS, you could use some other system. I personally use Sherpa, and that's distributed as CIAO too. So if you have all the previous stuff, you have all this. So we're going to load into number 1. We are going to load the PHA, all the PHA2 files. PHA2 is what we downloaded, and it's combined. It's actually a 6 spectra in it. And we'll start at 1 and has 6 spectra. There's fill IDs 1 to 6. 1 will be order -3, 2 will be order -2, 3 will be order -1, and so on. So we are only going to use dataset 3 and 4, which are orders -1 and +1. And then we'll also load the combined data and call it combined, so that, again, we can use it for plotting. So for 3 and 4, the ones that we use, the third and the fourth one in this PHA2 list, which will be orders -1 and +1, we are going to load then the ARF and the RMF. And so this is the LADG -1 ARF, the LADG -1 RMF, the LADG +1 RMF. And when you download the data, they sit in primary responses. So let's go ahead and load all that. And we'll also load the zeros order data here. So we have it. And now as we do Sherpa, and we'll do the analysis, we'll set it to wavelengths, because that's what we usually want to look at for grading spectra. And we plot dataset 3, which is one of the grading datas. Here we go. It doesn't look terribly good, right? You don't see terribly much. So what happens here is that specifically along wavelengths, there's no signal, there's 0 photons in it. So you see like these little dots and then arrow bars that go from that mark from around 0. And there's like 1 photon in here, and there's several of those next to each other. So what we're going to do is we're going to restrict the energy range to where it's useful, and we're going to group it a little bit. And then we'll plot it again. We'll plot the third, the fourth, and the zeros order. Here we go. So the order -1, we put a label on, order +1. See, like we do plot data, we put the label on here, so the label will show up later, and we know which color is actually which one. And we'll take out the error bars because it's hard enough to see already. And so here you see again the difference between low resolution and high resolution spectra that I talked about in the other video. The green one is a zeros order, and there's these whoopingly bright neon emission lines here. It's totally dominated by that. There's an oxygen emission line over here, which is absolutely there. But if you look into the low resolution CCD spectra, maybe you can guess that there's something here, or maybe not. It's hard to see, right? So there's additional information we get from the grading spectra that we wouldn't have from just the CT spectra. Here, there's separate lines. We're going to measure these 3 lines separate. And in green, it's like one giant mush that starts like somewhere over here from over there. So the order 0 is useful, but it doesn't give us the same information that we have. I want to show you another Sherpa trick to look into this a little better. There's different ways of doing it, but one way of making plots that we can like zoom in and out is to use the bouquet plotting package. It's integrated in Sherpa. We can set it temporarily for just one plot. Bouquet will be loaded. And now we get like the same plot, although the slightly different colors because we use different defaults. And we can go ahead and we can use the mouse to zoom in And now you can see that we have here, this is the zeroth order spectrum. You can easily see that this falls in 3 separate lines, like on a very low continuum or background over here. There's a small line here. This is the neon. This is neon at 14.45. This is neon. This is an iron line. It's actually an iron line in here, but that's very weak in TW Hya. This is neon. We can also zoom out again. There are different ways of doing it. If you have a mouse, like with a mouse wheel, for example, you can let's zoom into the oxygen lines over here. They're weaker because the detector doesn't go as much. But again, here's one line here, one here, and one here. These are 2 photons here. And so that's again one of these triplets, one of these ratios you want to collect. We can go and we can move it around. We can zoom in and out. And so that's just one other way to show it. You can also take this and export it to an HTML file and embed this into your journal article or embed it into your web page easily by just taking this plot back and the current figure and saving it to an HTML file with a .save command to save it into an HTML file. Okay, but we want to now go ahead and fit it. So let us look at this. We're going to define a model. So that let's go back to what we actually want to fit. And so for this particular notebook, I've picked out fitting this triplet line here, this triplet. And so we're going to set a model that has a Gaussian for this line, a Gaussian for this line, a Gaussian for this line, and like a constant at the top here. So that's a model that we're going to use. We're going to restrict our data to just that particular area and make a plot of it to make sure we picked out the right area. So this line, and this line are the lines that we're going to fit. And the model we'll use for that is a constant, and then deltas, just sharp lines here, here, and here. And we freeze their position at the known wavelengths. We can look that up in a table. I mean, I know I've worked on this for years, but you can look it up in Chianti or in APAC or in AtomDB. You can look up where these neon 9 lines that we want to look at, where they are. So we do them delta, which means an infinite width. They're like tiny, right? And that's because this broadening here in TW Hya, that's not actually from the start. That's a finite resolution of the instrument. Even though it's high resolution, it's around 1,000. It's not infinite, and it doesn't resolve the intrinsic line width. This is, in this particular case, for stars, at least for stars like this width here is instrumental. So we don't have to fit that. We'll freeze the locations because we know they don't move. We can look at it later and see if like maybe it's redshift or blue shifted. But I already know that that's not very likely here. So we'll start with simple model with just a couple of parameters. Let's do that. And then let's say it's the same source model here. We combine our source model as a constant and these 3 lines, and we set the same source model for the -1 and the +1. So we fit those, and for the combined spectrum that we'll use for plotting. Okay, let's go ahead, set the statistic to cache. Cache is a good statistic when we have low count numbers, because like here's 0 or 1 counts, right? So we clearly can't use Gaussian statistics. And then we're going to fit 3 and 4. And here are the fitting values. And as I said, we have to do the plot on the combined one. Oops, that looks bad, right? Really bad. Like the data is up here. In fact, like the data looks like this, but you see this goes up to 0.1 or so counts per angstrom. So it goes from 0 to 0.1. So in this scale, you can't actually see it. And here are those best fit lines. And instead of emission lines, the absorption lines that go to -600. So it's clearly bad. What happened? Well, and the starting values we used were just too far away from the actual values that we get out of the fit. And if you fit something and your starting values are too bad, the fit looks for the next minimum. It starts like it looks at the chi, not the chi-squared, but in this case the cache, the value of the statistics, as people know from chi-squared, and then it calculates the gradient, and it goes down that gradient in pieces trying to find the minimum. But if you're far away from the minimum, far away from the real minimum, it might run into some local minimum somewhere else, or just runs amok. So what we are going to do, what we're going to have to do, is we have to start the fit somewhere closer to where the real numbers are. There's different ways of doing that. You can have Sherpa guess it, for example. And then it's use some heuristic. Like if you give it a line like this, it'll just start with a maximum here as the fitting value, or we can just set that by hand. And so as I said, like here, like the real number isn't going to be minus 600. It's going to be close to like 0.1 or something like that. We'll fit it. We don't have to have the exact number. We just have to have the right. We can't be off by several orders of magnitude. Then things go bad. Okay, so we're going to go for all three lines and we're going to set the amplitude to start with at 0.01, and we tell it we are looking at emission lines. So don't give me negative values. The minimum that we can accept is 0. Maybe the line isn't present, but it's not going to be an absorption line. And if we go ahead and fit that, and you see the values come out here at like, they're not at 0.1 because of normalization and the width of the lines and stuff, that comes out at -5 or so, but that looks way better. So here the final value of the statistic after this fit is about -500, like -142. Whereas if you look at this fit, the final fit statistic is way worse. It's like 36,000. The fit just ran in the wrong direction and didn't happen to find something. Let's calculate the confidence on those things. So we get some estimate of the errors, and then we'll go and plot it. And so again, I use the plot fit here, and then I do get current access in matplotlib and add some extra matplotlib commands to modify the plot that Sherpa gives me. I do that by setting the title and then by putting some labels on. And here we go. Here's our best fit. So this is the R line, the I line, the F line. I put a label on, and you see this time it's a beautiful fit, right? Maybe this is offset a little bit, and working on these stars for a long time, I can tell you what's happening. Here's like a weak iron line that we didn't fit, that we didn't include in our model, but it's weak. And you see the height of this thing is pretty good. But if we were to include this weak iron line here, and include this weak iron line over here, we'll probably get a slightly better fit. You can do that. You can do more sophisticated things, but the purpose of this tutorial is to show you how it works in principle, and then you'll have to go for your particular source and put the right model in for your particular source. So I'm not going to fine-tune this too much now. Okay, so we want to keep going in Python. We've calculated the confidence values that are printed to the screen here, and that's good for looking at, but that's not so good for continuing with it and for doing it. So I'm going to get a Python structure confres here, which saves all that stuff, and then get the parameter values for the fitted parameters 1, 2, and 3, which is these three amplitudes. Parameter 0 would be this constant that I don't care too much about. And we're going to get the maximum values so that we can use it as an estimate for an error. And then we can do some grading. We can do the ratio, the F plus I over R, and the F over I, which are ratios that will tell us something about the density and the temperature of the plasma that emits this. And we'll also do some like error propagation, some simple error propagation, not statistically correct, maybe fully, but for this tutorial, it's good enough. It's not statistically correct because here I'm assuming Gaussian errors. I just do Gaussian error propagation. Good enough for plot. Okay, so the flux ratio F to I is 0.7 plus minus roughly 0.2 or so. And the ratio of the F plus I over R is again about 0.7 plus minus 0.1 or so. We're going to take that and look it up. Now, in order to look that up, we need to know what the ratio should be and how this ratio depends on the density and temperature. And we can go and look that from an atomic database. I have used, in this particular case, the Chianti database. There's a package called Chianti Pi that you can use to access it. There's several other ones. It's not in the scope of this tutorial to explain exactly how I did that. You need to check out the Chianti. If you want to do the exact same thing, check out the Chianti documentation. But the point is, I wrote like a file here using Chianti that gives us the ratios we expect for a given temperature and density. So we load this file, and then we can, again, I'm skipping over the details of how I set up that plot and how I made like the labels there on that plot. And we can make a plot like this. So this is our measured ratio, right? If we go up a little bit here are those numbers, 0.74 and 0.65 with some error bars. And that's what I plotted here. The F to I ratio here with some error bars, and the F plus I over R ratio here with some error bars. And these gray lines here are from the Chianti database. That's from the file that I load in. The lines over here are constant temperature, and lines in this direction are constant density. And you see the area where we found the best fit isn't actually covered. Maybe it moves a little bit if we include that iron line in the fit. But like within like about 1 sigma errors or so, we are somewhere in this region. So we can say we are hot. We are certainly not up here where it's 1 megakelvin or less, or 2 megakelvin or 2.5 megakelvin or something like that. We are somewhere down here that's 10 megakelvin, that's hot. And we are somewhere in this range where the densities are high, between 10 to the 13 and like 10 to the 12 or so. Right? If we won't know if we are exactly here or here because we have error bars, but we are certainly somewhere in this high density region. Now remember that TW Hydra has observed doing a number of times, and I picked out one data set to run this through this example. Now we can do that for all the other ones too, and I've done that. I've measured that in the same way using the same code. And so I'm just going to give you the answer how those look and not run the same thing all over again. But they can be all reduced the same way, or we can download it and get the ARF and the AMF files, and we can go ahead and use Sherpa and fit that, and then we'll find something like this. So that's the same like this black one over here. That is 13.50, which is what I've made gray here. And so I read off the temperature here, here, and I read off the density from these lines and the error bars, and then I put it in there in this plot. Okay, and I do that for all the other ones too. And what you see is like a rough correlation here between density and temperature. Well, what does it mean? I don't know. That's why it's called research, right? We aren't done yet. But an idea would be that this accretion stream where mass falls onto the star has like a dense core where it is hot and dense. And when we see that dense core, depending on what the geometry of the looking is, then we see something that's hot and dense. And if we happen to look at a different time where the viewing geometry is slightly different, where maybe we see it from the side, then we might see the outer layers of it, which are less dense and less hot. For example, that's one idea. How could we test that? Well, we can measure not just neon triplet, we can measure the magnesium triplet too, we can measure the oxygen triplet. There's more diagnostics in the spectra we get. And we can measure, we can use, like we didn't use the amplitude yet, we just use the ratio between the lines. We can also use the amplitude to tell us something about how much mass falls in at all, right? Because if more mass falls in, more X-rays come out. If less mass falls in, less X-rays come, fewer X-rays come out. And so we could do that too and tell us if that's consistent with this idea. Now, there's a science interpretation, right? Again, the purpose of this tutorial is to tell you how to reduce grading data. So I'm not going to do that, but if that's what I'm going to continue to be working on to make this project scientifically worthwhile. So I want to give you just some conclusions to go away with. Stars form in dense clouds of gas and dust, right? They accrete mass from the disk, and those disks ionize the disk. They shape how that accretion proceeds. X-ray grating spectra are a powerful tool to study this accretion in young stars. And in this particular case, we see like a high density, which is a signature of that accretion shock. And we find that the density and temperature are calculated. Now, summarizing all the data sets and all we have about gratings, although I've only run through one example here, right? We have the HETG, which has 4 spectral arms. We have the LETG, which we used here, with 2 spectral arms. These things can be run either with ACES, which has energy sorting, gives us zeroth order spectrum, or with the HSC. And if you go back up to the table at the very top, you'll see that all these combinations here have actually been used for Chandra. Here's an LETG HSC observation with HSC as a detector. Here's an HETG with ACES. Here's an HETG with the HSC. So depending on which wavelengths you actually want, what's most important to you, you can pick different combinations of detectors. In principle, the data reduction works in a very similar way. There's a couple of special sources topics that didn't apply in this particular case, right? We can look at PyLab for bright sources. It's not the CC mode. Extended sources are a little different. But I hope I could show you how, at least for one case, we can go down, we can download the data, how we reduce it, what chow commands are needed, how we can call those chow commands from Python, and then how we fit that with 1 or 2 examples of what can go right and what can go wrong in the fitting process. Thank you.